Hi, welcome. So tonight we're going to be working on the memory allocation scheme for the new node-based material system. So the way it's currently done is, if we look at this, so each BSDF node basically, let's look at the construction. So if we look at how we construct them, we basically just mix and match and combine them, and each of these kind of new constant texture, they allocate stuff. Same for new diffuse, they all allocate stuff. And the way I want it to work is, instead of having to have this, destroy pointer on the BSDF, then for each of these types, we're going to have to, give them their own destruction function and, set it and then handle all that. That's a bunch of extra effort for just no reason, because we can just use like a shared memory pool and just have them all allocated on there. And then once we're done with them, we can just free the memory pool and then be done with it. So this new memory pool can be used for all sorts of things. We're just going to start with the new material system and then eventually maybe use it for other things. But yeah, so that's kind of the goal today. We're going to get rid of all this, destroy, diffuse, destroy all the, bunch of extra code that we don't really need to write. So first we need to actually implement the thing. So I didn't invent this structure. This was pointed out to me by a friend. I'm just gonna write it for this project. So I guess this can go in utilities. I don't know, maybe, yeah. Let's do it here. New file. I'm gonna call this mempool. It's gonna consist out of these blocks that are then singly linked together. You'll see what I mean. So a block, let's see if we can even make this. I looked at this implementation for a bit and it kind of made sense, and now I'm trying to implement it. So a block has a size, it has a capacity, and then it will have a pointer to the previous block. And then it'll have the actual data. And now this is going to use a flexible array, which is a thing that's allowed in C99, but we can't use, this needs to be like aligned properly. I'm not entirely sure on the details, but it needs to be aligned. So we don't have like max align T in C99. So we're just going to borrow from hash table, use a similar thing. Yeah, we don't have max align T, so we have to create a type that has the largest alignment requirement. So we're just going to kind of yoink that. So it has a size, a capacity, pointer to the previous block, and then the actual data. And then we can just, basically, we can allocate a block and then just allocate extra space after the block to contain the data we want. So, and then the API, first of all, we want to create a new block mempool thing. And this will take a pointer to the previous block and the size of the allocation, the initial allocation you want. We'll call it initial size. Then we'll want a function that destroys the whole pool of memory. So then just the pointer to the head. You'll see what head means in a moment. And then we want the actual allocation function, which just returns a block of memory. What should we call this? Alloc in block? No, alloc block, I guess. I'm not good at function naming. They should be like all consistent to like, but yeah. I think alloc block is short and nice, maybe. So for this, it's gonna take the current head, and then it's gonna take the size of the allocation you want. So it's sort of like malloc, except we had to pass in the list of blocks or the memory pool, right? and it just gives you back, you know, a void pointer for the memory. Okay, that makes sense. We'll try and make it. Let's see if I can make it. So first of all, we need includes for all the types and stuff. Let's set this up like that. So to make a new block, we'll just do the initial allocation. Size of new block, and then plus the initial size. So this is where we allocate the extra space for the whatever data we want in there. The initial size can be just like an arbitrary value, I guess. We'll see how it ends up being. So capacity will be whatever the initial size we give it. Size is the currently occupied size, how much stuff we got in there. It's going to be 0 for this. And then the previous pointer is just going to be the previous we pass in. Right. So we pass in. The usage will look sort of like, it's going to look sort of like pool is new block, and it's gonna, you're just gonna pass in null for the first one because we don't have the first block yet, and then we'll do like a kilobyte, and then the thing you want to allocate, I guess we're gonna have to, thing is calloc block, and then you can pass in the pool. And then whatever the size, so size of struct foo, and then do whatever you want, and then the end destroy blocks, and then pool, something like that. That's what the goal is. Right. For the destroy blocks, we're just gonna walk from the head backwards to the beginning of the list, and then free all of them. So. Well, we have a head. If we don't have it, we just return. So while we have a head, we get the previous pointer. Add previous, and then we just free the head. And then we set the head to the previous. Pref? That doesn't make sense. Prev. There we go. So yeah, we just grab the previous pointer before we actually deallocate the head, and then, you know, continue, just loop backwards and go through the previous pointers. And then for the actual allocation, well, if you just pass in 0, I'm just gonna return null. That's easy. And then to do, right? Let's not do that. So if whatever you're trying to allocate is bigger than the current capacity of this block, then we're gonna have to add a new block to the end. Figure out the size of that. So if we add a new block, we're gonna have to modify the head, update the head. So this is gonna have to be a double pointer. So if the head size plus the size of the new thing is greater than the capacity of this block, then we have to need to add new block. So we're gonna have to figure out the size. So the size of the next block, and then it's gonna be like the minimal size. So if like the head, if the current head capacity is like bigger than the size, Then we're just gonna return the capacity of the head. Capacity. Otherwise, just the size. So if the size is bigger, does that make sense? Yeah, either the capacity, this is like sort of a min. Yeah. Yeah, okay. And then the head will be, we're just gonna add the new block, right? New block. How we can use this function now. Head, and then the initial size is the next size for this new block, right? Okay. Yeah, we need to do this. And then, if we don't need to do all that, we're just gonna basically get the pointer and then bump up the size, right? So head data plus the head size, and then add the size, right? Yeah. Head size, size, and the pointer in this. When you need to cast this, I think it doesn't complain about it, but conflicting types. Oh, right. Oops. There we go. Build failed. What happened here? Oh, I messed that up. Okay. Let's run this in our head. So we get a new allocation of like 10 bytes. Yeah, that goes clear. So this, whatever the size of this one, plus size. So yeah, if it fits in this block, we're just gonna skip all this. We don't need to add a new block. Then the pointer is gonna be just the head current data. So the head of the head. This is kind of the head of this head block. Plus the current size. So that's where the new data is gonna start. Store that in here. Then we have to increment that size by the new size. So we tell it that it's, you know, increased in size, the occupied space, and then return the pointer. Okay, does that make sense? Let's write a test for it. Make sure it works before I actually start using it. So the way tests work in C-Ray is a bit funky. Basically, I wrote the test system myself. It's very simple. We have the actual tests list here. So this is the list of all the tests, the name, and then the test function. And then we have a thing called test runner that knows how to run all the tests in different ways. So you can run a script like run tests, which compiles it in, I think, debug mode, and then just runs all the tests one by one in separate processes. So yeah, it uses some flat command line arguments to run just a single test per run. So if one crashes, it doesn't crash the whole thing. So yeah, we're just gonna make a new test. I don't know if it's a good system, but it seems to work, and I had a lot of fun making it. So we're gonna make a header file, test mempool, add them to both targets, I guess. Yeah. Cool. Just gonna yoink something from. Yeah. Okay. Yeah. So let's skip this. So bool test mempool, and this is gonna return the if it fails or not. So this is just how it works currently. If you have ideas on how to make this better or like nicer to look at, feel free to let me know. So I just initialize this to true, return passed, and then I run my tests. So there's a tests assert script, which I need to grab the test first of all. Test mempool. Not found, huh? Text mempool, that's not right. I messed that up. Yeah. Does that work? Right, and then let's see. Test assert, there we go. So the test assert is that in the test runner. Yeah, if it fails, then we'll just set the pass to false and then store the failed expression so we can print it out. So let's make a memory pool thing. Let's see. Source utils mempool. What is memory.h? I have memory. Do we have a thing called memory? What is that? Oh, I think, yeah, I tried to make like a malloc wrapper a long time ago. It's not used anywhere. I should probably delete that. I was trying to do like statistics of like how much was allocated and freed and stuff, and then it just didn't pan out. Yeah, I should delete that. But anyway, mempool. That's fine. So if we know how to use this. Yeah, so pool. We'll call this a pool. I sort of consider it to be like a memory pool. You just put stuff in it and then single free. Don't have to worry about it. So new block. We don't have a previous block, so we're just gonna give it null. Then initial size, we'll just do like 64 bytes. We'll make it real small. So let's see what happens if I try to first of all like right away allocate something bigger than 64 bytes. Let's just imagine how this works. So make the new blocks, and then we make the new block, and then call alloc block on something that's bigger than 64. So the head size, so this would be 0 plus 60, like let's say 128. It's going to be bigger than the capacity. Then essentially the first block will end up being empty, right? That's kind of wasted space, so it makes sense to make it a little bit bigger. So I guess I'm going to go with like a 1 kilobyte block. I don't know, just feels right. And then in the end, we're gonna destroy blocks pool, and then we're gonna put a bunch of stuff in here. Let me grab some types so we can just store them. What would be like a big one? I don't know what we want to store in here. How about like a render tile? Let's put render tiles in there. Source data types tile.h. Yeah, we'll test it with that because the tile contains a bunch of members that are not just pointers. Yeah, it's got a bunch of crap in there. Will that work? Yeah, okay. So let's put, how should we do this? So let's just put one in and see if it works even. Tile is alloc block, then the pool, and then sizeof tile, right? And then tile, we'll set something. Tile, and whatever. Something that we can recognize. 99, something like that. Tile. I don't really care about 1337. I don't know if this test even makes sense. It's gonna be 69 wide. And then, first of all, let's make sure tile exists. I mean, obviously this is gonna work, but again, access like 1, whatever. I just want to get my bearings right. Pass. Oh, it's pass, not past. Cool. Yeah, we do need semicolons in this language. Take the address of the pool. Okay. Then the way you add this to the test list, you just copy the name and then put it in here. And pool. What should we call this? Because there's only one test. Mempool works. Test mempool. Cool. Let's try and run the tests. Okay, mempool works. So that's good. Maybe we should do something more creative. Let's do like a loop. Let's just put a bunch of stuff in there. Like ints. Right. Pass, yes, true. I feel like I suck at writing tests still, but I'll get better. newBlock, null, 1024. We'll start with that. And then destroy blocks, pull. Then here we're just gonna do amount. We'll do like 1,000,000. Something like that. Maybe we should do like debug prints. Should we do that? Let's not do that. At least not yet. If we run into issues, we'll do debug prints. I'm double checking that I'm recording because the last video I hit the wrong button. I hit start streaming instead of start recording. And then it went to Twitch live instead of recording it. So that was fun. I had to rip it off Twitch and then upload it to YouTube. That was a dumb mistake. But now we're recording. So, oops. List an amount. And then, first of all, let's stuff. Wait. We'll just do a bunch of tiny allocs. So, test tiny. Right? So we could do this in like one big call of like just, put in, 1,000,000 ints all at once. Then that's going to make one big block, right? So the first block will be empty, but then the next block will just be the whole thing. So let's just try and make this so that we just call alloc block a bunch of times and see how that works. And then we'll do another test where we run it like just one big allocation. I don't know if these tell me anything. Big alloc. But yeah. So this would be like we'll do int alloc block the pool and then amount times size of nums, right? That should work. And then this wants to take the, wait, what? What happened here? Struct pool. Oh, I'm not calling it the right thing. It's a block. Yeah, and then this will want a address of the thing because we can update that. So here, let's see. How do we want to do this? I guess we can just ignore whatever the return is for this. Can we? Pool. Should we do like an initial thing? we'll do one allocation first. So we get that sort of head. No, because we can't. Yeah, we're gonna have to keep track of the actual pointer to the data that we want. We have to store somewhere, right? So this is just gonna be a test of how it behaves when you just fill it up. We're gonna not actually access the data, but we will be able to free it, hopefully. So sizeof int. Yeah, we'll call that 1,000,000 times and then destroy the pools. Can we do like test insert pool? We could count the blocks, right? We'd have to walk the list. I don't know what testable there is, like what we can test. But I guess we could compute the size of how many blocks we have and just see what it is initially. It should be, I think, in this case, we can fit 1024 divided by, I think int is 4 bytes? Is int 4 bytes? I completely forgot right now. Int, it's 4 bytes, right? Yeah. So 1024 divided by 4, we can fit 256 ints in the first block, 256 in the next block. So we should theoretically get divided by 256 blocks, right? And that doesn't divide equally, so we're gonna have to go a little bit over. So I'm gonna say 3,907, maybe? Maybe? 3,907. 3,907. We have to count the blocks, so pool block amount plus and then pool, yes, pool prev, right? And then block amount is, I'm betting that that's not gonna work, but that's my assumption right now. We'll see what happens. So 2 tests, one big old allocation right there, and we actually keep the pointer so we can actually access that memory. I think we'll just be able, yeah, we'll be able, this will just be like a normal, buffer. So let's put these in the test list and stop this. See if we can get this working. So mempool big calloc, and then mempool calloc test tiny. The naming is usually, yeah, we'll do mempool, which is a bit dumb, and then mempool big calloc, mempool, yeah, these prefixed by the actual file name basically. So mempool mempool big calloc, and then mempool tiny. Cool. Let's run those tests. Drum roll, please. I'm gonna bet that, oh, look at that, it actually worked. Did I actually get that right? Is it really 3097? That's cool. That didn't work. I need to pass in. That's gonna be test number 39. This is a bit derpy. I do this. 39. 3097. It counted the, yeah, of course. Yeah, okay. So yeah, I actually understood So if we take a look at the current head, oh, we're actually losing the pointer to the, what happens if we do, oh yeah, right, we're actually modifying pool here. We should do that. It ends up being null, so has pool, use that. There you go. And then we should be able to check the capacity of the last block. Let's see what happens there. So the current size is 256. Yeah. It's slightly over the, it fills up all the blocks except for the last one where it's 1/4 empty. Yeah. Pool size 256 left over. Right. Maybe that's a good test. I don't know. I haven't written enough tests to like really get like a good eye for what good tests are like. So I just kind of wing them and see. Cool, but that works. Tests actually pass. So maybe we can start using it. So now that we have this mempool thing, what is this? Yeah, I hacked the mesh loader earlier because it was giving us some trouble. I'm gonna point out that this time, let me pull this up. Man91 has been helping out recently. He built a brand new hash table. That's like way better than the previous implementation. It's like generic. You can actually use it for a lot of stuff. It's way better written than I ever could. It's pretty nice. And so we'll be able to use that for a cool feature in the future. So this is the first step of making memory allocation for nodes better. We're gonna, instead of basically building like a tree of nodes and then just traversing that tree to free the memory when we free all the nodes, we're gonna turn this into like all the nodes into like a graph, and then all the nodes are stored in this memory pool in the scene, so we can easily free them. But beyond that, that's what we're gonna do in this video. We're just gonna put them all in the shared memory pool. In the next video, I think, we'll do a technique called hash consing, which is a term I've never heard before. But basically what it means for this, it's usually like a programming language technique. Yeah, in functional programming. But we can actually adapt it for this. Hash consing is basically when let's go to an example. Assign. When we create all these new shaders here, new diffuse, or textures, indeed. If we create two diffuse, so like BSDF, struct BSDF A, it's gonna be a new diffuse. It's gonna have like a constant texture, new constant texture of like without color. And then we make a new one, like a second BSDF B. That's also gonna be the exact same thing. So right now, the way it works is these will just, this will return a pointer. It's going to allocate it, return the pointer. This will also do the same. So we're basically duplicating the amount of, like doubling the amount of memory we need for this, right? So with hash consing, we could basically detect that, okay, we already made this one. And so in the next call to new diffuse, we could find out, okay, this is going to be identical. And then return a pointer to the previous one that we made instead of just making a new one. I don't still fully understand it, so it's not going to be in this video. I'd have to read up on it a bit more, but that's going to be cool. We'll basically be able to just minimize the amount of memory we spend on building these graphs of nodes. But let's get back to memory allocation. So first of all, we're gonna make a pool in the scene. So let's see. Scene H. So this is gonna own the memory for the nodes, right? We'll put them in here. So first of all, okay, we're gonna include this struct block node pool, we'll call it, and then yeah, that's good enough for this one. We're gonna have to tell it to get the new scene, I guess. Load scene. Right, this is where we allocate a bunch of stuff. So we're just gonna allocate the pool here. We'll see where this goes. Node pool is new block. So here we're gonna need new block. No, we'll make it a kilobyte initially. Cool. And then in all these nodes, we're gonna have to pass in the node pool to this. So let's see how this works. So BSDF, first of all, let's get rid of the old code, I guess. We don't need that. It's gonna break. Cool. We no longer will need all this stuff. So destroy glass, don't need that. Do we need it? No, we don't. We'll need another pool for the texture nodes, I guess, because this is different. Well, maybe not. Actually, yeah, we can put it in the same pool, I guess. We can put all sorts of things into this pool. So no, we don't need that. Destroy glass, remove all this stuff. This is why we're doing this, by the way. We can get rid of all this stuff. I just built this because it was like the most obvious thing. But this is a lot of code we won't have to write with this new system. Destroy diffuse, don't need that. I guess also in the headers we're gonna wanna modify those. Let's see, BSDF-H, destroy BSDF, don't need that. Save for diffuse, yoink. 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 And yoink. And yoink. Cool. Then, what's happening here? Don't want that either. Bunch of Go we can delete. Destroy texture node, destroy checkerboard. We don't want to do that. We don't want to do that either. Nope. Yeah, texture node is also gonna have that, doesn't it? Yeah, destroy. Get rid of that. Yeah. Yoink. Anything else? Yes. Yoink. Destroy constant texture. A lot of code. We can delete that on this one. Destroy image texture. Yeah. Yoink. So any assets, we don't actually have any assets stored in the BSDFs. They're all just like their own things. So we don't really care about freeing stuff inside. We just want to free them themselves. Cool. That looks much cleaner. We don't have to worry about destroying that stuff. So let's see. Material, destroy material. Destroy material. Destroy BSF. There we go. Yoink. Yeah, we don't even have to worry about this. So if we destroy a scene, then we're gonna have to destroy the destroy blocks, scene, node pool. So that's basically all we have to do to free all of the nodes. single line of code instead of all that stuff I just deleted. So let's make it work. This works now, but it's going to leak a heck of a lot of memory. So we will do this. So let's see. When we're constructing any BSDF, we're going to want to pass in the pool. So in here, we're going to include the pool here, I guess. Mempool. And then just modify these. So these are all going to take struct block pool. Right. Same for new diffuse. Just an additional parameter. That's a small price to pay for this kind of stuff. New mix. Constant. New mix. Put all the stuff in here at once. Metal.h. There we go. Oops. Same for texture nodes. We can actually just stuff them all into the same memory pool. We're going to use this for a bunch of stuff in C-Ray in the future. I'm just starting out with this. Constant texture, checkerboard texture. Yeah, cool. Texture node, this one, this one, this one, and this one. Yeah, same for plastic. Cool. Nice. And instead of calloc putting on the heap, this is just gonna be calloc block pool and then size of new, just like that. Yeah, the address pool. So we might be able to, might have to. Oh, actually, this is gonna have to happen. Yeah, we're gonna have to do like this actually, right? So new plastic, it might modify the pool. All these might modify the pool. Okay, that's annoying. I just pasted a ton of crap. Okay, we'll just work it one at a time because we need to write this stuff. Cool. So let's work it one at a time here. Then texture node. Oh, this is annoying. Should have realized that. Okay. Pull. Calloc block. Pull. Size of new. And then we're just gonna pass the pool back in here. Pass it along, pass it along. What is the conflicting type? Oh, wait, what? Pool? Checkerboard texture. Oh, not visible outside of this. We'll worry about that later. Let's go one at a time here. Pool, pools. Right. Cool. Oops. Yeah, this is all like, wait, why is that? Where's texture node.h included? Let's see. BSDF includes texture node. Struct block. Show me this warning, please. I want to know where it's included from. Include it from here. Material.c. Yeah, okay, we can just throw a mempool in here. Include .details mempool. And then same for this one. So poly path trace. jeez, these are all fun. Texture node. Yeah, well, let's just put the thing in here. This will have to be removed anyway. Cool. Redefinition of block. Oh no. Oh no. Bad. 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 Oh, okay, we'll do this. Just throw a bunch of... yeah, okay. Yeah, okay, cool. We can just move on. Those are always tedious to figure out. Those kind of include things. So, calloc block, pool, size of new, and actually I can just copy this, can't I? Right. It's always the same anyway. Like so. Also add the star. Sometimes peek at my keyboard because it's like a weird layout. And the mic's right in the way. Yes, so cool. Warning BSDF, assign BSDF is gonna have to take a pool. Where's assign BSDF call from? Oops. I have to pass that boy along. Yeah, scene loader. Cool. You can just pass it from here. Yeah. Node pool. Cool, and then this one. No, it's gonna have to take that one, doesn't it? We'll figure this out. Eventually. Slowly. We'll figure it out. Pool. 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 You get a pool. You get a pool. You get a pool. Let's see. You get a pool. You get a pool. There's a lot of pools to add, but Powell? Oh, right, yeah, we got passing him. You also get a pool. You get a pool. Oh, new constant texture. This is... Wait, what? Node reviews. Oh. And then... Will this work? No. Pool. Cool. Slowly we gonna work through all the issues. So what happens here is a new diffuse does not want to take a pool because... Oh, BSF derp. Derp. Cool. Too few arguments to this function call new constant texture, new pool. Wait. So this one expects 4, and it has 3. Right, it's this outer one. It takes a pool, texture, float, new checkerboard texture, pool, texture, size. Looks all right to me. Don't know about you. A new color checkerboard texture, pool, size. Yeah, that looks right to me. Pool, that one, that one, that one. What's wrong with that? Is that an extra thing? No. What's wrong with that? That one. gets pulled down, gets pulled. That looks correct to me. I don't know about you. We'll worry about that in a bit. Assign BSDF. Wait. And I know that because it's gonna include. Why does it no longer show which? So material.h. It's not in here. Oh no, yeah, material.h and then sphere.h. And then yeah, okay. We can just do struct block, can't we? New mix. That takes that one. Same for this guy. And bool. This is a neat trick that I like, is you can just dereference this and it'll give you the type compile time. That's cool. You don't have to worry about if this type changes, this will still work. Oops. This needs to star right there, and then here as well. Cool. Slowly the amount of errors is going down. We'll be able to test if this leaks memory once we're done implementing it. But we'll see. If we're really lucky, it's gonna work first time, but I don't think it will do that. Let's see. So this still is not happy about. Let's see. Struct block to new glass. So we gotta fix that. Take one of those and one of those and one of those. Same for new metal. You get a star. You all get pools. All of you. Kind of grindy sort of development, but we'll get through it. Pool. We're just gonna pass the pool around all the way to the constructors, but that's the price we gotta pay. It's a small price. Let's see. Assign BSDF. Oh, let's see. Pool. And yeah, we take the address here. That's cool. Yeah, same for this one. I think that's, yeah, because this pool, well, this is kind of the head, the latest block, this pointer. So whenever we add a new block, this will change. So yeah, cool. What is the deal with this? New checkerboard texture. Too few arguments. The function call expected for. We have 3. Let's see. Let's count them. 1, 2, 3, 4. Am I just missing something? Then oh, this new mix. There. Okay. Yeah. There we go. That caught me off guard. Oh, look at that! It built. Enum render type. Did this happen before? Oh, right, because we're including it here now. You know, let's not do that. Let's not do that. Let's just delete this test. It's kind of useless. I don't like that test. Yoink. Cool. Let's actually see if it runs now. Let's just do input HDR. Let's do 10 samples. It crashes. Well, that's logical. Let's see why it crashes. We'll do HDR. We won't test this time. 10 samples. Yeah, let's do that. Okay. bad access. So node size plus size over the capacity. Okay. Oops. Oh, don't do that. Oh, that's null. From where? Oh. Wait. So this is in parse JSON. Okay, so this happens right away, basically. I think I did something really wrong. Let me make sure that I have the thing. Lock block. So yeah. This will take that one. No, we want to take the. Let me think. I think we're passing the pool in incorrectly. Yeah, I think like in here, you're gonna want to take just a pool and then do something like this, right? Which is unfortunate. So I did have it right the first time, I think. Yeah. Okay, let's fix that. Okay, let's just go through them one at a time. Okay, let's do this. Pull there. Yeah, like that. I think. Yeah. I think I know what's wrong. Again, tedious kind of development, but make mistakes, gotta fix them. Oh, we didn't even change that one. So let's see about this one. We get the pool address. Pool. Yeah, there we go. Pool address. I'm sure you get the gist. The address of it there. And then what happens here? Right. And then one more here. How did I miss this? Texture node, okay. New constant texture. What happened there? Wait, new constant texture. How's that different? What am I missing? Oh, right. Just passing it along. And then, yeah, maybe that'll work. Oops. Oh. I just sent an IRC message by accident. Okay. What does that do? I figured, oh, look at that, it actually fires up. That means the allocator is working. We'll see about the freeing. Didn't crash, that's cool, but let's see. Scene loaders. 899. Why does this not warn us? Remove that. Why does this not warn us? That's kind of weird. I guess. Huh. Oh, where's the other one? 1022. This one warns us. Okay. Let's see about this. Pool is null. Ball is null. Ball is null. Oh, RC. Let's see. Node pool. That is null. So at this point, when we're loading, right. Okay, so let's see. Load scene. We parse the JSON before we allocate the node pool. That's a no-no. Maybe that will work. Oh, I sent the message. Let's just... Okay, there you go. Wrong terminal. Let's close that terminal entirely. That's better. Okay. What happens now? Actually gets to rendering, and then what do we have? We have a null pointer, don't we? BSDF. That is a not null pointer. What's actually the problem? Let's see, insect. Material. Okay. BSDF, all looks good. Oh, the sampling function is null. Oh, jeez. What's happened there? Let me think. What did I change about that? It would be really useful if we knew the type. It's a plastic shader, okay? Plastic, let's see. BSDF sample, plastic sample. Why would that happen? Plastic sample. Right, so it's a plastic material, but it is reflective, and the color is grayish. Okay, so it's the white sphere. How did that happen? That's kind of weird. How'd that end up being null? That is strange. Yeah, it is it's, let's see. Yeah, it's this sphere right here. It's white plastic, like whitish plastic. But why does it end up being null? That's not good. Like here, we set it here. Right. Actually, we're gonna start here. Assert map BSDF. If it doesn't have one, we're in deep trouble. Maybe that will work. No, it still works. That's weird. Maybe. Oh, we have heap corruption. Okay, that explains it. if you get this, you know, bad access at like a completely random point, that means we got heap corruption. Let's figure that out. Asan. Oops. Asan. Add our sanitizer. It'll basically just tell us on which line we messed it up. And there we go, right away. Assign BSDF 63. 63. Right here. New constant texture. So it's a new constant texture. And on line 98, here we mess it up. Why do we do that? Heap buffer overflow. It'll imply that this is not returning us a valid pointer. But why? Size a new constant texture. I cast it. That looks correct to me. So 2328 is a wild pointer. Okay, heap buffer overflow. Why would that happen? So we literally just overrun this for some reason. What do we get from this? Oops. Let's just stop it here. Let's do this. What does it not know the type? Oh, it's broken. I don't know why LLDB does this. It just does expected type, like size of int. Oh, well that works, but basically it just bugs out just expected type. I don't know why it does that. Maybe like an optimization thing, I don't know. That's not gonna help us. Why would that happen? So what happens here? Get a heap buffer overflow, let me think. So get the material. What is material at this point? Roughness. Is this last sphere material? New sphere material is, yeah, it's a member of the struct. It is not allocated in any way. It's just kind of created default material. Yeah. Okay, that's reasonable. But what happens here? Pass in the node pool. Node pool. Size of 24 still has plenty of capacity. It does the first block, in fact, because basically the first thing that ends up getting parsed is the spheres. That's just how it's structured. So we know this happens right away at the beginning of parsing. We're literally just the first. So it did make the allocation. I'm going to bet that the material is... So I'm going to bet that this is going to be 24 bytes. That's 24 bytes. Okay, so we made the allocation. And wait a second. Let's see. So make an allocation here. So if the size is 24, right, and then the pointer is gonna be the data plus size. So isn't it true that for the first allocation, we end up no, it doesn't. Yeah, it returns to head. So the size. Wait, no. So this data starts here, and then we add 24 and return that. So doesn't it just miss 24 bytes? So the first allocation is just 24 bytes into the data buffer. I mean, that shouldn't matter here because we're still clearly in this heap buffer. But that's kind of weird. I have to look into that. Do we have to cast this? So it notes to go by bytes. Right, because this is like, you know, whatever size that is. I don't know. Wait, we got past it. Did that fix it? Right, because this is this plus size. It doesn't know what size steps we want to go in unless we specify it here, I guess. Right? Yeah, we'll still get some bugs, but at least he got the rendering this time. What happens if we just do a release? Sometimes it works even though there's like some weirdness going on inside. Okay, so now it actually gets to rendering. We have to fix that ASAN bug, but of course, but cool. It actually works now. Okay, so yeah, it just wasn't iterating this correctly, which for our tests doesn't bode well for a test. They should not have worked. Test mempool. How would we test that? I don't know, but this definitely worked, even though that was obviously wrong. Will the test still run? Yeah, they pass. Okay. Well, we figured that out fairly quickly. Let's do ASAN again. I do want to catch that bug. Run that. Gets the rendering, and then it does something funky. Eventually. This is a really long line. I should. Okay, so what is this? Ignore that. Read points to 0 page. That's not good. So since this happens in the actual rendering, there's multiple threads doing this at once. So that's why it says, you know, found another one ignoring. Thread created by this one. Yeah, whatever. Sample shiny plastic C33. 33. So it tries to evaluate the roughness, I guess. Plastic PSDF. Let's see. Plastic.c. So it just takes the roughness, sample shiny, passes in the BSDF, and then it does a plastic BSDF. It tries to get the roughness here, even though that's null. So it should be null. Oh, right. Okay, I know why that happens. Okay, so the reason why this happens now and it didn't before is before we callocked here. So all the memory is 0 allocated, right? But now inside here, we call malloc. Where is it? Inside here, newBlock. We malloc, so that's not guaranteed to be 0. So this roughness thing it might be, you know, a broken pointer. Okay, so there's a couple ways to go about this. The first would be to do like new call like roughness is null. That would fix it, but I don't feel like doing that. I'm just gonna modify this and use calloc, right? Yeah, we'll just gonna use calloc, initialSize, sizeof, newBlock. That should fix it, I think. I have a feeling it might fix it. Let's see. That's my theory, anyway. This will be much cleaner, because seriously, we don't have to worry about destroying any of this stuff. It'll add a lot of flexibility in the future for doing more cool stuff. Come on, you can do it. Okay, it actually got to rendering. I think that works. That is memory pool, a memory pool implementation, and now all the materials are on there. Let's see. Let's commit this, and we'll test if it actually works. We'll see if it leaks memory. That's the kind of test. So let's just make a commit here. Let me make sure all this is good. Why does page down not work? Seriously, why does page down not work? Oh, this is annoying. I'm just gonna use source tree. Good. Good. Yep. Yeah. Just making sure there's no like extra stuff I don't want to commit. That looks good. A lot of code deleted, but some added. A lot of code changed. Cool. Add some tests. Cool. I guess it's A. It's a chain of blocks, so my mind goes to calling it blockchain, which is not what it is. It would be great if we were looking for like investments in C-Ray. We could say it has blockchain technology, but let's not go there. All right, pool for managing storing nodes. Pool implement. I'm going to start all the nodes. There. Works. Great. Cool. Okay, so we're going to commit this and push. And then I have a Linux server because this is Mac OS, and getting Valgrind to run on Mac OS is kind of a pain. So the way I've been doing memory leak testing is I just use my Linux server called Triton. So git status, git pull. Yep. Okay, and then I just have this Valgrind script that just makes it. I guess it is it's in debug mode. I should do there should really be a real debug Valgrind. So yeah, it's gonna basically run it with like just 50 by 50 pixel image, single sample. It's gonna run real quick because running things under Valgrind is really slow. So this runs the memcheck tool. I could add it to also do like UB, but I won't do that. I'm just using this for memory leak checking basically. And it also uses a suppressions file, because at least on this Linux distro, like dynamically linking SDL, there are like ghost memory leaks that aren't actually memory leaks. I guess that's what the internet told me. So we just use the suppressions file here that I generated earlier. So it won't show me those. But it will show me the memory leaks that I've created. So I think there might be some even before I did this. So, but we'll be able to tell that. This will take a while. So let's just admire some code with that. I won't do the hash consing in this video. That'll be the next video. So in the next video, when we are done with that, when we do all this building these, because these will all eventually be built dynamically based on the config file. Right now they're all kind of, you know, discrete right here, but we'll be able to mix and match and combine things and do all sorts of stuff. So once we do the hash consing in the next video, hopefully, you know, if we already have made, it'll detect if we already made this node, and it'll just return a pointer to the previous one we made instead of allocating it again and again. So that way we use the minimal amount of memory. So basically different materials can share their nodes. It's like a graph. Instead of previously this was a tree structure, you know, every node contained their own things and we had to traverse the tree to free the stuff, but now it's all in the same shared buffer, but it's still kind of like a tree, is it? I guess it is. But then once we do the hash consing, then it's more like a graph, so we can have, you know, a single node point to multiple different ones instead of having their own. I'll have to learn about it a bit more. This line of code is really obnoxiously long. We can make it shorter. We'll worry about that later. Maybe we could call pool like P, because we're always... Ooh, look at that. 0 bytes. That is a win. I'm going to consider that a win. Suppressed 85,000 bytes. That's all the leaks in the thing, like the implementation stuff. New hash table is leaking. Still reachable. I guess we're just not freeing this. But this is completely unrelated to what we just did in this video. So first attempt, no leaks, memory pool, that is a win. I could end the video here, but we're gonna figure out this hash table leak. Let's see. So new constant database, parse args. Right. Okay, so it does it twice for some reason. Why does it do it twice? Oh, new constant database. This was modified by Madman91. So let's see. New constant. This is really not related to this video, but hash table C 54 and 52. 54 and 52. Buckets, calloc. Oh, I guess these are not freed, but whatever. That's not related. I'm gonna fix that off the video. If you made it this far, this is hour and 23 minutes. I thank you very much for your interest. Hopefully, it was captivating, making a cool little memory pool and actually using it. I'm gonna use it for plenty of other stuff once I actually find a good use for it. Where did I put that thing? I thought it was in here. There we go. Cool. So yeah. Until next time, hopefully it's going to be that cool hash consing video. We'll see. But yeah, thank you very much for watching. Goodbye.